I say. So let's talk about the next section. So this is 2.8. So we're going to talk about a forced harmonic oscillator. So this is the forced harmonic. All right, so we're forcing a harmonic oscillator. So now we have our mass y double prime plus our cy, which is our damping coefficient, right? Plus our ky, which remember this is our spring coefficient, equal to, now we're going to force it in your book. We're going to force it at some cosine omega t, right? So we're going to force it either with a sine or cosine function. And we're going to transform this equation into the following equation. We're going to say py plus qy equals f naught cosine omega t. And all we're doing here is p is equal to c over m, q is equal to k over m, and then f naught is equal to f1 over m. Okay. So let's see if I want to say how to explain this. I do a fun little trick, and I have a half hour to teach you the fun trick without getting you lost. Or do I want to teach this without getting you lost? All right, let me do a little sidetrack. So here, this is what we're going to solve. Now, technically, we should be able to solve this, right? Because this is just an integer. This is just an integer, right? Because our mass will be some sort of, or not an integer, but some real number, right? It's just a constant and a constant. So we know how to solve this because we can solve the homogeneous equation. We just learned how to solve this, right? We just learned how to solve this. And your book does it crazy. But when we solve it, right, when we solved it before, let's see how I can do this. How do I want to do this? Yeah, I guess that's how I'm going to do it. All right. Okay, so we can solve this. But the problem is, so let's talk about let's talk about physics for a second. Let me talk about physics. So let's assume we have let's talk about different types of forcing. So if I force an overdamped system, so an overdamped system kind of looks like this, right? Now let's pretend I force an overdamped system. So whatever my initial conditions are eventually not going to matter, right? Because eventually, no matter what, if I have an overdamped, critically damped, or underdamped, right? They all eventually, whatever my initial conditions, eventually disappear, right? It all goes to zero eventually, if it's a real system and there's real damping. If I'm forcing that, it's overdamped, it might look like this. And then it'll enter some steady state where it goes up and down, right? If I'm underdamped, it might look something really weird, right? But eventually it'll get to a steady state based off of what? Based off of my forcing coefficient, right? So this forcing coefficient produces a steady state solution. So before, when we had a damped a damped harmonic oscillator, it all went to zero eventually, right? If I sent t to infinity, it went to zero. Now that I have a forcing harmonic oscillator, it no longer goes to zero. It goes to some sort of steady state solution. And that's what we're going to focus on in this class, is finding what that steady state is. Could you solve all of these? Sure, right? You don't need any extra. I don't need a new section for you to solve any of this, right? I just don't. You know how to do it from 2.7. So why do we talk about this? It's because we want to get to we want to figure out what is that steady state, right? We want to figure out what is that steady state. And your book just goes in circles when it teaches it to you. It just does, right? I want to do it in kind of a clear fashion. So let me ask you a question. Let me ask you a quick question. And then we'll get back into diving into the math. Let me explain kind of why I want. So let's pretend I have some y. So y, this is going to look like C1 E, and let's just say this is going to be E to some negative alpha x plus C to E to the negative. Let me just say, hold on, let me just do, trying to make my constants different. All right. Okay, Sx, and hold on, since we're doing time, let me put it in time. Right on the opposite layer so I can erase. All right, so my real solutions for my homogeneous are the following, right? I can either have this, or okay. Oops, no. Everyone by me that these are. So these are our three cases. This is my overdamped, underdamped, critically damped, and underdamped. And I'm going to say K here is positive, right? These K's are positive or greater than zero, because if it's a real solution, these better be to zero. And as I go to infinity, these go to zero. Now, if I add a particular solution on, y particular, my y particular is going to look like some A cosine of my omega t plus some B sine omega t, right? That's what it's going to look like. Because if I'm forcing if I'm forcing harmonically on an oscillator, this is what my solutions look like, right? So as t goes to infinity, this is going to go to zero. This is going to go to zero. Same with this and this. And since this real part goes to zero, all of it goes to zero. So I'm just left with this. We're going to call that our steady state. But if I told you, if I said y equals, oh, let's see how I can do this. Let's see if I can do this correctly. Oh no, I worked through it perfectly fine. So let me ask you a question, right? So let's actually do this. We have time. I got 25 minutes. So let's work through an example. And working through the example will help me to achieve what I want. But after I've established, so let's do an example. So we're going to do this example real quick. And I'm going to force it just with some sign forcing, something really simple, right? All right, so we're going to solve this. So step one, we want to solve the homogeneous, or y of h. Y of h here would be lambda squared plus 2 lambda plus 2 is equal to 0. That's what it equals. That means that lambda is negative 1 plus or minus I, And so my homogeneous equation here is C1 e to the minus t cosine t plus C2 e to the minus t sine of t. Okay. All right. Now, our next step would be to find a particular solution. So y particular. What would we guess in this case? What would we guess? What would we guess? Well, here I'd guess some k1 sine of t plus k2 cosine of t. Now, do I need to multiply by t here? No, because this is, I have e to the, that looks like, this is not, this is different than that. Even though it's sine of t, it has the e to the t on it. So you don't need to multiply by anything. And I solve for it, right? And I will, just to save time, I'm going to give you what the answer is, right? If we solve for it, I'm going to get minus 2 5 cosine t plus 1/5 sine of t. Okay. Now I'm going to say t is equal to 340, just out of just to be pretty long in it, right? 340. And so here, hold on, let me just make step 3. Let's put it together. So y is equal to c1 e to the minus t cosine of t plus c2 e to the minus t sine of t minus 2/5 cosine t plus 1/5 sine of t. And I say at t 140, what's the amplitude? What's the, where is it at and what's the amplitude? Well, here, I don't know if you guys really grasp a sine and cosine function can be really just written as a complicated sine function or a complicated cosine function with a certain amplitude and a certain thing. If I ask what the amplitude is after this point of my oscillating spring, could you tell me what it is? Does anyone? And the answer is probably not, right? Because it's not written in a form that you would really, because this might go up as this one, they might not never go up at the same time. They might go down and up at the wrong time and all this other stuff. So it could be just a big mess, right? And so solving it, is this correct? Sure, right? It's 100% correct. It is the answer to the system. However, it just doesn't give us that much information. So I'm going to introduce this idea is that the sine of, so let's pretend we have some k sine omega t forcing, right? I'm going to rewrite that as e to the I omega t, or k e to the I omega t. And I'm going to solve for this, and I'm just going to take the imaginary part. And the reason I do this is I want to put this into complex numbers. It's called complexification. And by putting into complex numbers, can I solve for this? Sure, right? I know how to solve for this. I know how to solve for, and so in our case, what we have here, we'll have y double prime plus 2y prime plus 2y equals, here it's just going to be e to the I t, and then I just know I want the imaginary when I'm done, right? Can you solve this one like you solved the other one? Yeah. And what you're going to get? Well, you're going to get, this is the same, right? This didn't change. Our y particular is going to be a different guess, right? We're going to guess, the y particular guess will be y of p will now be some complex number e to the I t. So we're going to guess that. And then at the end, we're going to take the imaginary part. So let's do that. So it's yp prime and yp double prime. Now this might seem crazy. Why is he doing all this extra hard work? Right? I e to the it, and this will be minus z. Nope, no more I e to the it. Now why would I do this? Well, this is minus z plus 2i. Oh, oops, I forgot. Got my e to the it. So this will be minus c e to the it minus 2 or plus 2 I e to the it plus 2z. Oops, I forgot my z in here. 2z e to the it equals e to the it. I can just cancel off the e's, the it's. And so I have, and I'm actually going to change, I say particular, but just let's make this a little bit more clear. I'm going to change my notation to a c, just so I know I'm in the complex realm. So what does this end up being? Z equals 1, because 2 minus 1 plus 2i is equal to 1. So z equals 1 over 1 plus 2i, or if I rewrite it another way, I'll get 1 minus 2i over 5. Okay, and notice if I, so that what z is, and so my complex solution is the following. Z, oops. Y complex is equal to 1 minus 2i over 5 e to the I. And notice that this answer here gives us this answer here, right? If I plug this through and take the imaginary part, because this will become cosine plus I sine, the i's multiply together, give us the positive right here, and then this that gives us a negative plus, and then this comes together, gives the positive sine of t for the i's, and we can get that solution. Oh, I might be in deeper trouble than I think. How many people know how to to convert a complex number into polar coordinates? I'm in deeper trouble than I think, ain't I? I assume things. Hold on. All right, so see if I can do this in the polar as fast as possible. I can do this. I don't think I can do this in 15 minutes, but then we'll be done. So let's just do this. All right, so polar complex numbers. I knew I might be in trouble. I didn't know why until now. All right, so here if I have this to be alpha, so this length, oh, hold on. So if this is my alpha, this is my beta, right? And this is my magnitude of my z. So here, if this is my real part, this is my real plane, this is my imaginary plane. So every real number will have some real part plus an imaginary part, and I can put every imaginary number on the complex plane. Have you guys seen this before? Vaguely? Okay, so some people have at least seen this before. Therefore, z, the magnitude of z is just alpha squared plus beta squared. Okay, that's pretty simple. The this angle here, this angle phi here, this angle phi is equal to so tangent of phi is equal to, hold on, very, very careful about this. It's equal to opposite over adjacent. So beta over alpha. You have to be careful when solving this because if you just take the arctangent, you may not get the right one. I have complex notes to give you guys. I might have complex notes to give you guys. Let me take it through. And so here we can write this in complex terms. And the reason we want to write it in complex terms is very, 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 for a very simple reason. So I'm going to go back to the one we were working on. I now have this. I'm going to rewrite this as in polar form. And it seems like a lot of work, and it is. I'm not going to lie to you. But if we rewrite this in polar form, the magnitude of z would be 1/5 squared plus 2/5 squared equals, so this would be 1/5 squared plus 2/5 squared, right? Square root. Because it's the square root of alpha plus beta. Okay. This ends up being 5 over 25 or 1/5, so this equals the square root of 5. Okay. My phi here is equal to, since we're in the first quadrant, or since we're in a nice safe quadrant, I can just take the arctangent safely. And so the phi here is equal to 1.107. Okay. And so this number turns into, oh, and when you write it as 1 over square root 5 e to the I. You write in polar form, z is written as the magnitude of z, e to the I phi. And so this is e to the minus, oops. This is e to the minus 1.107. I'll do another example of this. Oh no, I. And then we're going to multiply that by e to the it. And then I can put these two together, so I get square root 5 e to the I of t minus 1.107. But now, when I convert this over, into sine and cosine, this is 1 square root 5 times cosine t minus 1.107 plus I sine of t minus 1.107. And so, and I just want the imaginary part. So my particular solution in this case, if I just take the imaginary part, would be 1 over the square root of 5 sine of t minus 1.1. And I'm going to tell you this is, I wouldn't say infinitely, but much more useful of a particular solution than this. Why? And I can tell you exactly why. What's the amplitude of the steady state? It's 1 over square root of 5. That's the amplitude of the steady state, right? You can easily say that when you wouldn't really know how to pull it out of here, right? Especially if you have a weird omega, right? What's my phase change? Well, my phase change is right here. And so let's get back to the notes. So get back to the notes. So here, if we do this, how to get the amplitude, we need to convert to polar. We just have to do so, right? And so we convert it to polar. And we get this solution because we just want to take the imaginary part. And so we get our particular solution here. Or if you really desperately want to write in cosine, you certainly can, right? You just use the conversion. This time when we put it together, when t goes to infinity, this part's going to go to 0. This part's going to go to 0. So this part's hard for you to visualize, and it's hard for you to do this. This, however, is not, right? you can easily say, what's the amplitude? The amplitude is 1 over square root 5, right? What's the phase shift as an angle, right? So the complex works the same for both cases. So, so I go through another example. So let's take off the damping for a second, right? And we're just forcing a normal one. Here, we'll get the solution, but notice for these, we don't have our, here, we do not have our e to the t because we don't have any damping anymore. This will just oscillate back and forth, however the initial conditions state they will. We want to find one particular solution. In this case, we're going to be forcing it with cosine, so we're going to take the real part of omega t. You run through the same song and dance, you get this answer, right? And we have this. And so this is my real solution. However, notice what happens if omega gets really, really close to square root of 2. Well, this term does what? It blows up, right? And in fact, if it is square root of 2, we can actually redo it all. And then we'll add, in order to redo it all, we have to enforce this t right here. And the t blows up, right? And so what you have here is it falls apart. Your bridge falls apart. But this is what all I'm going to force you guys to care about, right? Amplitude and the amplitude, phase state, and steady state. So generally, I work through all this, right? Your book does not do this, right? I work through all this mess, right? So given this, and so given your Q, P, a Q, and an F naught and WT, I worked it through because like you can do this generally. You don't need to do it anything fancy. I work it through generally, and then I solve for the amplitude, right? This is your amplitude. And it simplifies to this. So your amplitude is the absolute value of F naught times the square root of 2 things squared. So it has to be positive, right? So this is your steady state amplitude. And then tangent of phi equals this angle. Your particular solution is this. If it was a cosine. If it was sine, nothing changes. It's just it'll be the same number. It's just instead of cosine, you'll have a sine, right? And so I worked through the whole hard process for you. You don't need to do what I showed you to do, right? I know this is terrible, right? It's like, why don't you just show me at the beginning? I could have checked out hours ago, right? Because I want you to see where it comes from. So here, I've solved for it. Your book doesn't do this. I solved for the amplitude and the steady state for any stuff. What happens here is just if it's undamped, you can have what they call the natural frequency is what. So this is whatever this omega t is, whatever this right here, this is the natural frequency. We call this the natural frequency when we solve for it. This is the forcing frequency. When the natural frequency and the forcing frequency equal each other, what happens? What happens? Yeah, things go boom, right?